Ja, I think that's better. Then we can find out
I don't know, maybe.
Yeah. I'm gonna run hours. So I'm just gonna skip all the tasks. It means you can do like 3 hours in a day. But yeah,
You need one I can fit in the way.
This one has to go to the
Very good. We can start. We have finished well. Yeah. Where did Niels go? That's great. You're here. So I think we're good. We have enough chance, huh? Okay, cool. So there's two left. You don't have to sit on the table. There are two. Okay. So welcome everyone. Welcome here also to you there for those outside. So welcome to the Master's Defense of Niels van Veen. It's been a challenge at the start already when Niels approached me and asked me, I want to work on boomerangs as a topic. And that's, can we match this to like geometry processing and computer science more general? And I think it worked out quite nicely. It's been a journey over 9 months, and today we're at the final stage, and Niels is going to present the results of his work. Before we start, let me quickly introduce the committee. So we have Shukon Sang here, who is the independent external member. He's from a pattern recognition group and assistant professor there. And then we have Ricardo Marukim, who is also supervisor of Niels, and he's from the computer graphics group. And I'm Klaus Hildebrand. I'm chair of the committee, also from computer graphics. Today we'll first have a presentation where Niels presents his results. It's going to take up to 30 minutes, and then we're open to questions from the public. So everybody is encouraged to ask whatever they think is interesting to know more about. And then we'll retreat with Niels for more questioning with the committee. And then we'll send Niels back and discuss the grades, and then come back and deliver the grades here. And that all will take about 1 hour, roughly. So then you can stay here in the room and wait or get a coffee, and then we'll back the exam. So that's all I wanted to say before we start.
Hi.
Go to Niels.
Well, thank you everyone for being here. Let's make sure I'm in the camera. So first of all, I'd like to thank the committee for being here, and especially my supervisors for guiding me during the project. I'll quickly start with a quick motivation about the problem I'm trying to tackle, and then I'll show the table of contents before proceeding with the actual presentation. So I got, on the slides you can see many boomerangs, but these are boomerangs. You throw them and they come back to you, and they have an aerodynamic profile on them. But you get so many of them, and most of them are handcrafted by people, and they're over years of iteration. For example, Bill, that's one of my throwing teammates. He has boomerangs he's been working on for 5 to 10 years straight. So a lot of knowledge goes into these boomerangs, and trying to replicate them is quite hard. And what we want to do in this thesis is make new boomerangs based on these existing boomerangs, and find boomerangs that are in between them, because this one is really good, this one is really good, but they fly very differently. So we want to combine the features of them, and it means that you want to find points on boomerangs which correspond with each other. And that's called the correspondence problem. That's the major problem that has been tackled in this work. And the ultimate goal is to make new boomerangs, so 3D modeling of boomerangs. So first of all, I'll give some terminology about the work. Then I'll talk about the data set I had to create because there wasn't one in the world. Then I talk about how I tackled the correspondence problem and how we evaluated that. And then I'll talk about how we can create new shapes based on this data. And I'll end up with a small conclusion. So first of all, on the slides, you can see two boomerangs, the 2-wing and the 3-wing boomerang. This has 2 wings, this has 3 wings, and we mainly focus on these kind of boomerangs in this work. Every boomerang has a trailing and a leading edge, and here we assume a right-handed boomerang. Keep in mind, just remember these kind of locations, because I will refer to them later in this work. Then we got the elbow region, which is the intersection of the wings and the wingtips. Just keep in mind these locations. We're not going into any physics in this work. I'll just refer to these spots on the boomerang, so keep those in mind. Then the data set. So we got all of these boomerangs. I'm a competitive thrower myself, so I just 3D scanned my own boomerangs. And I mainly scanned 2-bladed boomerangs and a couple 3-bladed and some others for future work. Here in the work, we assume flat boomerangs, and I'll talk about that later on. Then the correspondence problem, which is a bit of a hard problem to get your head around if you're not very technical. So one thing to look at it is that, for example, the wingtips, they correspond with each other. And the outer elbow corresponds with the inner elbow. Those are a given. And you can have an educated guess on, okay, this is probably the right position on from one boomerang to another, if you want to find correspondences. However, it becomes very tricky when you want to find a point, for example, halfway the wing. For example, here, you don't know whether it would be here, here, or here. And of course, you can all do this by educated guesses and saying, oh, this is probably roughly there. But when you got more than 10,000 points on the boomerang, it becomes very tricky and you have to find a way to parameterize your boomerangs. And the technique that was used in this thesis is UV mapping. And I'll talk about that later, but first I'll show you a picture to make sure you understand what step we're going to tackle. So this is the correspondence problem. We want to go from a set of unorganized 3D boomerangs, which are scanned, to a set of boomerangs with one-to-one mapping between every boomerang. And here you can see some color coding, and where the color is similar, it means that there's a correspondence there. One easy way to look at it is if you imagine you have an orange. The orange is your 3D object, this one, and if you when you unpeel it, then you got this peel of the orange, and that's your UV map. That's your 2D representation of your 3D object. And what we'll try to do in this work is get the same peel of your orange for boomerangs. So you got 2 boomerangs, and you try to unwrap it in such a way that you go to the same outline of this peel of the skin. So that's the thing we are doing here. So the main goal is to find a UV map within the same outline. And the way, this is not a new thing to do. The UV unwrapping has been done before. However, if you do look at an angle-based way, for example in Blender, which is a 3D modeling tool, then you can see that the top and the bottom of the boomerangs are very, very clearly visible in the UV map. However, some areas like these lines, they are on near the trailing and leading edges, and you don't really know where they are. So it's really hard to say, oh, this point corresponds with this point on another boomerang. So that's why we got this work going on. I put some text on the slide to show you which steps we're doing, but I think I better just go over them. First, try to get a 2D outline of a boomerang and lift this 2D outline back to 3D to get a seam for your boomerang. The seam is basically a way to split your boomerang into halves. And then we get our UV maps with least squares conformal mapping, and with barycentric mapping we can get to correspondences. So the first thing we have to do is when you 3D scan boomerangs, they are all from different. You scan them from all different static positions, but when you reconstruct them, one boomerang is like this, and the other boomerang is like this. So you want to make sure that all boomerangs are facing from the same perspective, so from perspective. So that's done with fitting a plane to your boomerang, and then make sure the plane is perpendicular to your viewing port. Then we project it to 2D space. So these are our boomerangs which are in 3D, but if you shine some light on it and you look at the shadow on the wall, that's your 2D representation of your boomerang. So we want to go to the shadow in this case. Then with this shadow, we want to get the outline of a boomerang, which is this red curve. And the technique that was used to get this outline is alpha shapes. Alpha shape means that you have got your alpha, which is your radius of your circle, and you subtract all of these circles with your radius from your shape. So you can see all these points are your data, and you just subtract all these circles to get this outline. Alpha shapes really help because if you got a dense point set, you can play around with your alphas, and if there are more spacing in between points, you can have bigger circles. One of the criteria for these circles is that you need 2 points on your circle, then it's alpha exposed, and you don't want a point from your data set in that circle anymore. So here it's good, but here you can see there's a point in your circle, and then it's not good anymore. It's not your boundary. So then you just forget about it, not the boundary, we don't want it. And one way to figure out which of the 2 points you want on the outside of your circle is do a Delaunay triangulation. And with this Delaunay triangulation, you have shared edges, and on every edge you have your point A and point B. Those have to be on the outside of your circle. And in the slide, there should be a video to show that when you're playing around with your alpha, that when your alpha is very small, you get a lot of points in your data. And when it gets bigger, you will have less points because you get a lot of points within your circle, which is just the thing you don't want. I think this slide is a bit clearer. Here you can see that when you get bigger alpha, like now it's good, but when the alpha gets bigger, you seem to go away from your boundary. So you have to play around, tweak your alpha, make sure you get a proper boundary. Otherwise you can get something like the convex hull. Let's do that for both of our input shapes and make sure that they are sorted. So in this case, go clockwise direction over your points. And this will help with matching later on, because if one boomerang is a different direction, you don't know how to get your correspondences. And let's get back to those first correspondences that I showed in a couple slides before. Those are called landmarks. And those are our first correspondences for the boomerangs. So the wingtips again, and the outer and inner elbow. And what we want to do is we want to parameterize between these points. And one easy way to look at it is you want to go from point A to B. And if you walk on this route, you want the 50% mark of this route to be the same as the 50% mark on the other route. So for example, this is around 50%. This should also be 50%. And you do this for all your points, all your data, and then you get your correspondences in 2D. And here it's visualized with a color encoding. And you do this between all your landmarks. So you got all these as well. And you stitch them together. So then you got a whole parameterized curve in 2D. But boomerangs are 3D. So we have to go some way back to a 3D object. And the way we do this is we got these points and we want to lift them to make sure they are back close to a boomerang. But as you can see on the slide, might be a bit better visible here. You can see these points. This is our 2D curve and lifted. And you can see it's not on the boomerang itself anymore. This yellow thing that's the boomerang or 3D object. And the way we can go back to it is projecting it back onto the surface, which is visible here. However, when you project back onto the surface, there are a couple ways you can handle this projection. I put a couple of them on the slide. So these triangles are in 3D, even though it looks 2D. And this is, for example, your projected point. And this is your nearest vertex location. And you can either shift that vertex to the projected location or shift it to this vertex. Or you can retriangulate. And all of them work. I've tested them. However, I personally ended up with option A. I got the nicest, smoothest results on the boundary of that. One of the downsides is that you can get potential overlapping triangles. Imagine that you got a lot of projected points near this vertex, that this vertex might be shifted around a couple of times. You don't want that, really. But if you take option B, then you lose this information of this projected point, so you can get a very jagged curve. And the whole goal of this 3D curve on the boomerang is that it's smooth. If it's very jagged and then you try to get correspondences, your correspondences would also be jagged. So that's what you not want. And in theory, the retriangulation should be the best option. However, when you 3D scan boomerangs, if you look at this part of the surface, it's quite monotone. So the 3D scanner at some point says, oh, there are enough points. Let's not scan more here. But near these trailing edges and the leading edges, there are a lot of dense points because there's a lot of different curves. So your points are very dense there. And if you retriangulate, you make it even denser. And that means that when you go UV mapping, you could get inaccuracies because it's already very dense and it leaves more room for potential problems. So all of them work. I just personally went for option A. And then one technique to do UV mapping is least squares conformal mapping. Imagine this 3D globe. Let's see if I can just leave it. You got this 3D globe.
You can just click on it.
Yeah. So we got this 3D globe, and when this is in 3D and a 2D these are all 2D representations and they're all UV maps. However, some might be nicer than others, and in this work we choose for a way that it keeps angles between your arcs, and that's called conformal. And so this is a way a UV map of a conformal of a least squares conformal mapping technique. Well, the slides decide to
put your mouse back to your screen.
Okay, cool. So when we want to use least squares conformal mapping, we want to go back to, you get a UV map from your 3D object. So in this case, this is the first boomerang, and you can simply say, okay, let's just project it, and then you get a UV map. That's your orange peeled skin. And now we want to get the same orange peel, but for the other boomerang. And we already know, okay, this is how the orange peel looks like. So let's try to use this boundary, this red boundary, and map this blue 3D curve to it. And then when you use least squares conformal mapping with some constraints, you can keep it within this outline, but get a different UV map. As you look very closely, the triangulation is a bit different. And that's what we want, because now we have a shared space to find the correspondences. And one way to visually check if your UV maps look decent, you can apply some checkerboard pattern. So this is on the first object, shape 1. This is on shape 2, and you can see that the squares are mostly square. And that means that if you have squares that don't really look like a square anymore, then there's some distortion in UV map, which is usually a sign that there's something potentially wrong there. For example, when you use least squares conformal mapping, this is quite a good example. The squares look still square, or at least slightly stretched out, which is okay. But in this case, when you use as rigid as possible, you can especially see it here. There's a lot of distortion going on. So that's a quick way to check if UV map is okay-ish. However, in this work, we made sure that the view is on top of each other. So you got your top and bottom of the boomerang within the same UV map. That's a bit tricky. So if you just do the unwrapping technique in Blender, you can see top and bottom are clearly separate. On this work, the top and bottom are both on this outline. So you got overlapping triangles, and you have to make sure that when you do your mapping later on, is that you have your top, which is the red here, and you map your top to a top, and not a top to a bottom or a bottom to a top. So you want to make sure that you're not going over your boundary, so to say. And this is one of the more important slides. So when you got a point in your UV space, so this is a point from shape 1, and this is the UV map of shape 2. Put this point exactly on the UV map of shape 2. Get its neighbors where it's on the shared triangle. Find out where, in respect to this triangle, this point lies, which are your lambdas, which is this term. And then go back to these points, but in 3D, which are these points. And then use these points to interpolate and get your new location, which is the green point. It's basically just filling things into this formula. And here you can see that this point is still not on an intersection of triangles, but because this is the original input of shape 2. And when you use the faces of the first shape, then you can see that it's on intersection, which means that there's now one-to-one correspondence. And here it's a bit more visually visible. So these are 3D boomerangs, and you go from some point on shape 1 to some point in shape 2. And you can do this for all your points, so more than 10,000 points. Put some color mapping on it, and then you can see that, okay, well, this point corresponds to here. This probably corresponds to here. This to here. And now it's just the color mapping, but in theory, you can just say A to A, B to B. And you can do this for all your boomerangs in your data set. So all of these have one-to-one correspondences. You went from a 3D scan boomerang data set to a data set with one-to-one correspondences. So this point corresponds to here, corresponds to here, corresponds to here, up to there. So now we formed our correspondences. Then I quickly go over some short evaluation. I can't really go into too much depth here. But I evaluated on area and shear distortion and chamfer and Hausdorff distances. This is to check if the UV maps are still good. And with, for example, least squares conformal mapping, you want to reduce the amount of shear distortion. For example, the area distortion looks at that if you got a triangle, if the triangle gets a bit bigger or a bit smaller, so a compression and stretching. And most in the figure, you can see all those red parts are the noise. And after 3D scanning, sometimes I had to do some post-processing. And those are exactly near those locations. So that definitely affects the quality of the UV maps. And near the boundary, so these kind of locations, there's a lot of noise because it's very dense with the points. And the same story is for shear distortion. Sometimes it's a bit of random spots, the noise, but usually it's near the boundary. And then to check the quality of your second shape, because the second shape changes, the first shape you keep the same. You get a new amount of vertices and you use the faces of the first shape. So you have to make sure that it still looks like it's shape 2, even though it has a slightly different topology. You can do that with chamfer and Hausdorff distances, and in the picture you can see the differences. And you can see a very slight amount of noise here, but it's almost neglectable. And the results are very good for chamfer and Hausdorff distance, indicating that the shape 2 still looks like shape 2, which is good. And then the ultimate goal is you have all this data, and from this data you want to get new boomerangs. And that's why we form these correspondences. And the technique that we'll be using here is first get a template shape from all of these correspondences, and then from these correspondences go to different shapes. And later on I will tell you a little bit about how we can give a 2D drawing and get a 3D boomerang out of that. So that's this part, which is basically on this slide. So first get a template shape. You can see it as an average shape of your boomerangs. If you look on the left, these are all the boomerangs after your correspondences. Some are rotated a bit, some are translated a bit. And if you just simply take the average of all these correspondences, then you get a shape like this. And it doesn't really look realistic anymore. It's definitely not on the same scale. So therefore, first, I manually rotate the boomerangs. So they're a bit like this on top of each other, not like this. And then with, for example, iterative closest points, you can do the final detailed rotations at the end to make sure they're properly aligned. And then if you don't then simply take the mean of your boomerang, you get your average shape, which is a template shape in this case. We will start deforming our boomerang from this shape, which is on this slide. The technique that we'll use is principal component analysis. And the goal is to find different axes where the biggest variation is in your data, and use that to stretch out your boomerang a bit. So this is the equation we will use to get different boomerangs. We already got our mean shape, which is this one. And you can, from this mean shape, you should be able to go back to all your input shapes. But it means also boomerangs in between or still outside this range a bit, but still within your PCA space. And I'll quickly show an example of how PCA works. Here you have all those blue dots are points in your data. You've got your average point. This is around the center. And then the biggest variation is on this line. That's your very first principal component, PC1. And then the second biggest variation is on this axis. That's your second principal component. And all these points are linear combinations of the mean with something times the principal components. So you can get all of these points and back with a combination. I won't be going into detail how we get these principal components because it's part of principal component analysis. I can't really explain that topic in detail here, but I got them from singular value decomposition. The only thing that's still unknown is how we get the weights. And here I'll show you an example. So here I'm going to play around with the weights. We got about 12 boomerangs in our data set, so 11 principal components. And you can see that when you shift your weight per principal component, you get different boomerangs out of it. And this is all in 3D, by the way. And you can see that when you go to higher principal components, that the boomerangs get a bit more noisy. That's because they're capturing smaller variances in your data. So usually you want a combination of your first principal components, as I'm doing in this example actually. And you can see I'm getting quite interesting shapes out of them. And they're all based on the boomerangs from this data set. And then you can see I was playing around with a bit higher weights, and you can see there was some noise getting here because those are smaller variances in your data. However, that's cool. You can play around with the weights yourself, but how can we find a way to get these weights for you? So that's why one thing you can do is give a 2D drawing and try to optimize your data towards this 2D drawing to get that outline of the shape. And the technique that we'll try to use is, in this case, a gradient descent with a Jacobian term. Again, I can't explain it here. We don't have time for that. But you can see that this is the drawing, those red dots, and this is your template shape. And when you do principal component analysis with your optimized weights, then you get a shape that's a bit closer to this outline. However, you can see it's still not there. So we want something for the finer details, so to stretch it out a little bit more. And that's why we use a freeform deformation grid. So these are our control points in our grid, and we're going to shift these control points. And everything that lies within your square, or in this case, stretched out square, will deform with it. So that's a technique that's being used here. This is just a simple linear optimization problem. And on the right, you can see that when you use a 2D outline, so this is those red dots with a 10 by 10 grid, you can get very close to this outline. However, you can see it's still not there. You need some finer optimization to get it exactly within your outline. However, getting these grids is also a bit tricky. Here I show an example with 3-wing boomerangs. And you can see with a grid that's very small, it usually captures global variances in your data, so more global stretching out. However, when it gets a bit smaller, like a 10 by 10, you can see that it gets really close to these dots. But when you go have a bigger, even a more dense grid, it becomes more tricky. For example, here you can see it goes overfitting your data because it wants to capture very small points to your outline. That's not what we want. You still want it to look like a boomerang and not some piece of junk, really. Yeah, so I'm going to conclude the presentation here, and I'll start off with showing what I did. I went to 3D scan from 3D scan boomerangs to a dataset with correspondences. With these correspondences, I got a template shape and deform from there. And with freeform deformation, you can get new shapes using a 2D outline. Then there are a couple things for future work. I mentioned earlier for alpha shapes that you have to use a certain radius of your circle. However, with certain shapes, I should have an example here. These are close to the same shape. However, here it is a bit of room in the inner elbow. Here there's not. And with these kind of shapes, it's struggling a bit because it's hard to fit a circle exactly in this inner elbow. So I would recommend having a bit more of a dynamic alpha parameter in certain areas like the inner elbow. Then one of the assumptions with lifting this curve in 2D from 3D is that I put it halfway the boomerang. That makes it assume that I have a flat boomerang. For example, some of these boomerangs might not be very visible, but some of these boomerangs are tuned like this. So they're not flat anymore, they just are bent. And when you then project back to the surface, you're not getting an exact location that you are aware of where it is. So it might just not be on the trailing or leading edge exactly anymore. So that's something to work on. Then let me see, this is a good example as well. These boomerangs have holes in them. With least squares conformal mapping, it's very tricky to parameterize. So you either have to fill these holes or find a way to ignore them. So that's something to work on for future work, some non-genus zero boomerangs. That's what we call them. And the statistical methods that were used to deform these boomerangs are linear. I would look at nonlinear deformation techniques to get more accurate representations after stretching and deformation. So that's what I would personally do if I would have more time, actually. But that's the presentation. I wish we would have more time to go into depth about certain topics. But I would like to invite you to ask questions, if any. Thank you for your attention.
Thanks for presenting all your results. Now we're open to questions from the public. Everybody's invited to ask whatever was unclear. There's no stupid question. Anything that's unclear, please feel free to ask. Yeah.
My first question, well, first of all, thank you for your presentation. What I want to ask about is the landmark points that you mentioned.
Yeah. Shall we go back to the slide?
Not necessarily necessary, but what I really want to ask is, for me, of course, it's easy to visually see where the points are supposed to be. Did you manually insert them into the database, or did you find? Okay.
So the landmarks, in this case, the 4 points for two-wing boomerangs
Mhm.
are handpicked.
Yeah.
So that also is a bit of a tricky process because you have to you have a lot of points on this border, so you could just pick a wrong point. And if you pick a wrong point, so bad landmark, you get bad results.
Yeah, and did you have that during your research?
Yes, I had plenty of that. But after some time, you learn how to tweak the landmarks in such a way that you get better results.
Okay, interesting. Thank you.
Thank you for your question.
Well, it doesn't seem really a goal of your research. Have you thought about how they actually perform? Because there's no aerodynamics term in there. So,
yes, thank you for your question. That was one of the things I wanted to do, but after discussions with the supervisors, become a bit too broad if I would do that too during the project. But I've told about 3D printing them. I was working on the 3D mold to do carbon fiber layup, so then the boomerang would look similar to this. This is a carbon fiber layer. Or do some 3D simulations with it. Well, just to see how the flow is on the boomerangs. I haven't done that, but I think it would have been nice to look at.
all right. And a follow-up question: do you think, if you now know how they would perform, do you think it would be possible to integrate some term into your current work that could help your aerodynamic?
I think it's a hard question to answer because you need to throw it to see it and to experience whether it flies good. But my suspicion is that if one boomerang and one boomerang fly good, that the combination of them should in theory also fly quite well. But again, I need to test that on the field to make sure I can give a valid claim.
Yeah, thank you.
Thank you for your presentation, which is very visual and very stimulating. With your experience of throwing many, many hundreds of different styles of boomerangs, in your analysis and the shapes that evolved from your analysis, did you see any shapes that look fundamentally fresh and different from your experience that made you want to make physical ones and try them out?
Not necessarily, but I noticed that a lot of them end up with the same similar shape. So this template shape that was used, most of the shapes are very simple deformations from that shape. So I would say that everything within a small amount of deformations from this template shape produce very similar flights out of boomerangs. But I saw some interesting boomerangs with, for example, a very long second wing, where the first wing was a bit more stretched out near the wingtips. I think it's very interesting to play around with those kind of shapes.
And just to follow on, you studiously avoided anything to do with the aerodynamics because there's only so much you can do, I realised. But one would have thought that physically you'd want to incorporate terms like moment of inertia, inhomogeneities and density, radius of gyration, things like that, in order to perhaps take the candidate shapes that you've generated to see whether they look credible on those parameters, which you could calculate.
I think that should be very possible. Yes.
More questions? Good. Thanks everyone for participating and asking questions as well. For those that did. Well, then we'll retreat now to the committee and we'll be back in about 1 hour. So we'll stay in the room. There's the coffee sold and the if you want to.
Thank you everyone for being here. If there are any questions, I will be happy to answer them later on. Now I have to do the defense part of the thesis. So I see some questions in the chat, just ask them later. We can potentially schedule another session. Thank you.